Hello, this is Group 11, and our topic will be mechanics of fracture and failure in cathodes for lithium batteries. And our group consists of Andy, Jose, and Leo.
Before starting, we'd like to introduce the topics that are going to be discussed throughout, such as the basics when it comes to lithium-ion batteries, our focus on cathodes, the fracture, the microstructures, and then the performance improvements that are being done, and where the future of lithium-ion batteries and battery technology goes. To start off, we think it's important to understand some of the basics when it comes to a battery, such as the components and the process. So, the four main components of a battery are classified as the cathode, anode, electrolyte, and separator. The cathode, often regarded as the positive electrode, stores the lithium and releases the lithium ions when charging. The anode, often considered the negative electrode, stores lithium and releases lithium ions when discharging. The electrolyte is a liquid between the two, and it carries the lithium ions from the anode to the cathode through a separator. The separator, kind of like the name implies, separates the cathode and anode and keeps them from touching, as that would short out the battery, but it is porous so as to allow the transfer of ions from one side to the other. The infographic there on the right kind of shows the process of lithium and electrons moving from one side to the other. The basic process can be described as when we charge or discharge a battery, the lithium ions flow from one side to the other through the electrolyte, and this often creates certain stresses in the cathode and the other materials, mechanical stresses, thermal stresses, etc. Now that we've discussed batteries and the process and components that go into them, we can focus more on one of them being the cathode, specifically the cathode chemistries, as not all lithium-ion batteries are the same. Even though they might be called lithium-ion batteries, they might differ in ways such as the cathode chemistries, which all provide their own unique advantages, disadvantages, and the status that those are in. The table on the right shows you some of the cathode chemistries that are already out there and some that are being researched, along with the advantages and disadvantages associated with each, along with the fact that some have different status, such as being in consumer electronics, in EV, or still being stuck in research. One of the important ones to focus on is LCO, which is lithium cobalt oxide, and the reason for that is it's usually found in consumer electronics like phones, laptops, and cameras. One of the advantages of it is it usually has a higher energy density, high discharge voltage, and high conductivity, but it comes at the disadvantage of being made out of cobalt, which is usually expensive and toxic. Uh, Other cathode chemistries to focus on are NMC and NCA, which are nickel manganese cobalt oxides and nickel cobalt aluminum oxides, and those are usually favored in electric vehicles due to the higher structural stability that nickel and cobalt in the material provide. There's also an increased energy density when compared to others like LCO. Then there's LMO, which is not as popular in the industries, but is often seen in some areas such as consumer electronics and power tools. So one might ask themselves, why are there so many cathode chemistries, and why do we not just focus on one, improve it so that it can be used in multiple industries? Well, as discussed, there's utility. Each has their own advantage and disadvantage, and there's also supply chain issues. Unlike the fossil fuel industry, who has a supply chain that's been relatively stable and it's been around for over 100 years, the lithium ion battery supply chain is still constantly changing and relatively new. So, due to concerns such as the concentration of those raw materials, specifically in mining, processing, manufacturing, and also geopolitical reasons and ethical concerns of how it's mined, there's been a reaction to this. That reaction has been the want for newer research and the want for newer materials that are alternatives to this. Some of those alternatives they want are in cheaper costing materials or in metals that are in outside of these concentration points. The image on the right shows some of the concentration points in each industry, and as you can see in the mining, it's mainly areas like China, some areas in Southeast Asia, Australia, and Chile. And when it comes to processing, a majority of it is in China, with some in Europe and some in Chile. And cell manufacturing is limited to usually five areas: US, Europe, China, South Korea, and Japan. So it can be easy to understand that any disturbances in this relationship here of the supply chain can lead to big issues. And we actually saw this with the Russia Ukraine war that is still currently going on, as a few years back it actually ended up increasing the cost of some of the rare earth metals from those regions.
So studying fracture and failure mechanics in cathodes for lithium batteries. First off, cathodes in lithium batteries serve as a positive electrode and play a crucial role in determining the battery's voltage, capacity, and overall performance. Some of the main purpose of studying fracture and failure mechanics in cathodes is that it increases battery lifetime and durability, safety concerns, electrochemical performances, material selection and design, cyclability and rate capabilities, thermal management, and cost effectiveness. Overall, by just studying fracture and failure mechanics, it also improves battery performance and longevity. One of the purposes of studying fracture and failure in cathodes is because of battery lifetime and durability. Fractures and failure in cathodes materials lead to a decrease in energy storage capacity and a shortening of the battery's lifespan. By understanding the failure mechanisms, researchers can develop strategies to mitigate these issues and prolong a battery lifetime. Fractures in cathode materials can lead to reduced lithium ion transport and a decrease in the overall electrochemical activities of the battery, impacting its lifetime. So by studying these fractures, we can increase the lifetime of the battery and also increase the electrochemical activities of the battery, which improves the overall performance of the battery. Something else to consider is the safety concerns of batteries. Fracture and failure can lead to internal short circuits, which can cause overheating and even explosions in several cases. Understanding these failure modes help in designing safer battery systems. When damaged, lithium-ion batteries don't just burn. They can go into thermal runaways, an unstoppable chemical reaction where cells heat rapidly and begins to spew toxic and flammable gases. In the picture shown, it shows what kind of damage these lithium batteries could do when uh, when they fail. So by studying these failures and fractures, we can prevent these incidents from happening. Thermal management. So thermal management in lithium-ion batteries, especially at the cathode level, is crucial for performance, safety, and longevity. By studying the fracture and failure, this helps with cooling of the battery, preventing thermal runaways, and maintaining optimal temperature ranges. So in the image in this slide, it shows when under high temperature, PCMs begins to be melted, which absorbing latent heat and keeping the temperature constant. While under low temperature, PCM starts to be solidified, which releases latent heat and keeps the temperature steady. So one of the main reasons for studying fracture and failure in cathodes is because of cyclabilities and rate capabilities. Cyclability refers to the number of charges and discharges cycles a battery can undergo before experiencing significant capacity degradation, while rate capabilities describes how quickly a battery can be charged and discharged. Lithium-ion batteries experience mechanical degradation during cycling, impacting their performances. This degradation involves both intergranular, which means between grains, and intragranular, within grains, fractures in the cathode materials. These fractures are caused by stresses generated during the repeated insertion and extraction of lithium ions, leading to the formation of cracks and the eventual fragmentation of the cathode particles. The degradation of cathode materials through a fracture results in a decrease in active material surface area, hindering the diffusion of lithium ions and reducing the battery capacity. Additionally, fractures can impede electron transport, further impacting the performances. So by studying these fraction failures, we can prevent um, degradation from happening sooner, which improves the performance and the longevity of the battery. So currently there's some methods being used to study fracture and failure. So the first method is cohesive zone models, which have been employed solely for the examination of electrode particles during a singular charge or discharge step. However, it neglects the scenario in which these particles undergo cyclic loading and leads to fatigue damage. The other method is linear fracture mechanics approach, which examines the degradation behavior of silicon nanowires throughout the lithiation and delithiation process. And then the final method is phase field modeling, based on the regularization of sharp crack discontinuities by introducing an additional scale field, which smoothly represents the transition between intact and cracking state. This is used to model degradation mechanisms due to lithium process in lithium-ion batteries.
In order to fully understand fracture and failure mechanics in a cathode, we need to understand the three cathode material categories and their crystalline structures. So olivine crystal structures are characterized by hexagonal close-packed lattices. The octahedral holes in the lattice are then filled with lithium cations, which create one-dimensional channels that facilitate the movement of lithium ions during lithiation and delithiation. The next type is layered oxides, and these structures are composed of layers of metal oxides between which there is a one atom thick layer of lithium, and this allows for a two-dimensional movement of lithium ions. And lastly, there are spinel oxides, which have a face-centered cubic structure, which are formed by oxygen atoms, where the interstitial sites are occupied by cations, which provides a three-dimensional pathway for lithium ion travel. Now that we understand the crystal structure of cathodes, we can begin to talk about their causes of fracture. One of the major causes of fracture and a limiting factor on the lifespan of lithium-ion batteries is called lithiation stress. As a battery charges from empty to full, the cathode undergoes a volume change of up to 6.5%. This volume change is due to the insertion of lithium ions, and it creates stresses in the material of the cathode. Over several charging cycles, small cracks form and then propagate in the material. Fast charging actually exacerbates this problem because it creates an uneven distribution of lithium, which leads to swelling and fractures. The expansion of the cathode is non-uniform in certain crystal structures, which we'll get to in a little bit, which causes additional strains on the material. The structure of a cathode determines how well it handles lithiation stress. Layered structures experience anisotropic expansion during lithiation, which causes grain boundary fragmentation during its first charge. These cracks are then propagated in every subsequent cycle, and the battery performance decreases. Olivine lithium iron phosphate has shown promise and can undergo 30,000 charging and discharging cycles while retaining its starting capacity. Spinel structures undergo isotropic stress due to their three-dimensional diffusion of lithium ions, and this makes them a good candidate for withstanding stress from lithiation. Below is a chart that shows a decline in performance of a lithium-ion battery that has a layered structured cathode at 1, 50, and 100 cycles. To address the individual shortcomings of each crystal structure, you can use a cathode with a combined crystal structure. One study simulated the performance of a cathode using a combined layered and spinel oxide microstructure. The study determined that a combined microstructure decreased the stress in the cathode during discharging. This decreased stress then led to an increased performance of the cathode. So by researching combined microstructures, we can leverage the benefits of each microstructure to create an overall better cathode. For instance, you could use the structural stability of olivine or spinel cathodes to reinforce the layered cathode, which has a higher energy capacity. And below is a graph from the aforementioned study, and it shows the stress generated in the cathode for different blends of these spinel and layered structures. Aside from blending different crystal structures, there are several other ways to improve the performance of a cathode. Use of a single crystal architecture helps to ensure that uniform stresses occur throughout the material. Reducing the charging speed of batteries can limit the occurrence of fracture due to uneven lithium distributions, which is something that we talked about before. Coating the cathode in a shell of a more stable material can help to mitigate the effect of volume changes, and it can reduce the occurrence of particle fracture. Decreasing the particle size can also improve fracture resistance because smaller particles have a faster strain relaxation.
Material selection and design. So material selection will strongly influence the performance, safety, and the cost of the battery. Using recycled materials offers several benefits: resource conservation, reduced carbon footprint, waste minimization, cost effectiveness, and supply chain integrity. The chart shows a material formula used to form cathodes, and it also shows the cost, energy density, thermal stability, and cycle life of each material.
Now that we've discussed some of the topics regarding cathodes, their fracture, how we're detecting them, and what's going to happen, what is the future of lithium-ion battery and battery technology looking like? So there are still challenges facing the lithium-ion battery industry, and there's still current research going on for what the future might be. Some of the challenges being faced are those environmental impacts, recycling, volatility in the supply chain, greenhouse gas emissions, and legislation. Whether lithium-ion battery technology improves a lot more is gonna depend a lot on legislation and what countries want, and whether we'll have the materials to meet those needs in the future will also depend on how we're able to recycle the material. Some current research of battery technology that might be something to look forward to is that of sodium ion and lithium sulfur batteries, which are expected to make up 23% of the market by 2040. Sodium ion batteries are a lower cost competitor to lithium, and the supply chain is not as volatile. They can be made on existing lithium ion battery lines, which makes them more attractive. Lithium sulfur cells, they could enable a very high energy density and would be useful in high energy, low power applications. And then there's also research being done into lithium rich cathode materials. The image on the right shows how European battery demand is expected to increase from 2025 to 2040, and the different types of chemistries that are expected to make up that. It's hard to go by without hearing about AI and its uses in many different industries, especially now in engineering where it's being used for pattern identification and being able to get rid of what were previously labor-intensive tasks. There's a setback with being able to enhance our performance of lithium-ion batteries, and being able to understand the microcracks and their effects on a battery could be very beneficial to improving on what are already optimized methods. So, what are the setbacks with detection currently? Currently, imaging experiments are time-consuming, labor-intensive, and because a person is doing them, subjective. So AI is set to change that by assisting, as it's already been used in material research for being able to analyze very large data sets and provide some results and pattern recognition. Our understanding of fracture could allow for improvements in the manufacturing process of cathodes, which as mentioned are already optimized through trial and error throughout the years. On the image on the right, you see a deep learning model that was used by a group to be able to analyze micro cracks and come to the conclusion that will be discussed next.
AI detection using deep learning has already been applied to understand the fracture of lithium-ion battery cathodes. A team has used deep learning to analyze tomography data, which is used to create a 3D crack distribution by combining all the merged slices. 2D slices from the 3D crack distribution were taken using nanoscale hard X-ray phase contrast holotomography, which was fed into the model, which then analyzed the images and created density graphs of each section. So the model found that particles close to the separator show more severe damage compared to those near the current collector. The model also found that depth-dependent patterns indicate that cathode damage is non-uniform. And it also determined a relationship between particle packing and particle cracks. The lower the particle packing, the fewer particles undergo the reaction of lithium deintercalation with high kinetic rate, which stresses the crystalline structure.
So in conclusion, the study of mechanics of fracture and failure in cathodes for lithium batteries significantly impact battery performance and safety as shown throughout this presentation. This is due to factors like stress induced by lithium-ion diffusion, particle fragmentations, and damage to the electrode structure which leads to capacity fading and potential thermal runaway. So by understanding these fracture and failure, we can develop more durable and safer batteries. Thank you for listening.
That's all for our presentation regarding cathode fracture and failure. We appreciate your time, and these are the references we used throughout our presentation. Thank you.